Go. It said go. All right, so what did we remember or learn to be careful of last lesson when we're expanding? When you say brackets, what do you actually mean? Keep the bracket, that's right, when we've got this minus here. So are we pretty good now expanding this reasonably quickly? So if we look at x take 2, x take 5, did anyone come up with a shortcut for how they can expand that pretty quickly? There's silence. So I can look at that and say, well, that's going to be x squared take 7x plus 10. Right, so now people are going, yeah. So how are you doing that? And if people aren't doing that, listen to the shortcut. Do we know? Yeah, you add them together. So when you've just got a single x here, the shortcut is that you can just add these together. So minus 2 plus 5 gives you minus 7. And then you times them together, you get the last bit there. Now, if you're not comfortable with those shortcuts, get jiggy with it. But you can always do it by the long loop, loop, loop. So with this one, what would be my shortcut expansion? Yeah, I can see lip reading there. X squared, take 5x, because you just add them together, and then you times them together to get the plus 4. And you can double check that if you really wanted to by doing the long sweep. So as you were, x times x is x squared, x times minus 4 is minus 4x, then we get the minus x, and then negative times a negative gives you plus, and minus 4x take 1 gives you that minus 5x. So as you are doing them, you get that shortcut, because soonish, as in next week, we're going to be going backwards. And you want to go from this to this, and it's a shortcut if you know about the sum. It's called the sum and the product. Anyway, we're making sure we keep our bracket. So we're saying we don't have to write any of this down. This is just recapping what we already know, one hopes. And now we're taking everything through. So it's take x squared, take 5x becomes plus 5x, take the 4, becomes, so take and then plus gives you the minus, and then we just gather our like terms, correct? 1x squared, take an x squared, no x squared, minus 7x plus gives me minus 2x, and minus 10 take 4 gives you 6, and we're done. You might be thinking, why have you put up this other one? It's exactly the same, and I guess technically it is, but we're getting now to the point where we look carefully and we might recognize some things. So do we recognize anything with the second one? Okay, but we had minuses there as well. What's the big difference? Okay, they're switched around. Anything else? Yep. Yeah, these are actually the same. I like how you said that. Both pairs are the same, except for a negative and a positive. Oh, and you mean even those. Yes, jolly good, jolly good. So that actually is a form. It's a special form. What's it called? Difference. Difference of two squares. So if you can remember and you recognize difference of two squares, it means that you can do a bit of a shortcut. Right? A times A, that gives you the A squared. A times B gives you plus AB, but then you minus AB here, so they cancel out and you're just left with A squared take B squared. So again, this is a time-saving issue. So I can straight away go, well, this will be 10 squared. Do you want to put 10 squared or put 100? 100, okay. And then I can just say, well, that's now going to be minus x squared squared. What's that? To the power of 4. Very good. And then I'm going to go minus. I wrote 2. I meant to write 4. Thank you. And then minus, we're still keeping our brackets. And again, we're recognizing this is difference of two squares. So 10 times 10 is again 100. Negative times a positive is a minus. Oh, what's that one? 3x squared times 3x squared. 9x to the 4. So I didn't have to do all that middle bits because we know when we're looking at them they cancel out. Now if you did the long-winded expansion, you'll find they all still cancel. You'll get the same answer, but you've just taken a little bit longer. So 100 take 100, they disappear. What would I be left with? Right, you've got a minus and a minus, which makes a plus. So minus 1 plus 9 gives you the 8x to the 4. Agreed? Agreed. So that's the stuff that we should have looked at from last lesson. And if you haven't, when you find a little bit of time this lesson, please go back, practice some of them. If you just do one, that's not enough. You have to do it so you're fluent with all of this. Now, you will continue to get fluent with this when we look at one like so. When we've got a linear times a quadratic. I see, oh, shocked eyes. And you go, oh, same process. Nothing to worry about here. We're still just going to go, right, x, everything. No. Use my colours properly. Right, everything in this bracket here, the big bracket, everything is going to get times by x. Then it's going to get times by 3. So, am I good? Yep. So we're going to go x times everything, then 3 times everything, and it's going to be easy, easy. And again, I don't think you need to copy this down if you don't want to, because I will put a copy on our OneNote. It's up to you. I'll give you a moment if you need to, but times everything by x, we get x cubed plus 2x squared plus 4x. And then we're timesing everything by 3, so 3x squared plus 6x plus 12. Then we have to gather our like terms. Zoe, are we watching? Looked like you were looking out the door then. Now, yeah. Obviously, you can also have a quadratic times a quadratic, and it just becomes long, long, long. So you would then have, let's say you had another like 2x squared here. You'd have to then times everything in here by 2x squared, so you get another 3 terms, long-winded. You can make mistakes really easily. So there's a little check that you can do, and again, take it or leave it. But this is what we call synthetic multiplication. So see if you can figure out what I'm doing. Where have I pulled those numbers from? And let's use nice mathematical language. Yes already knows. Rowan?
It's like the numbers from the second.
Right. 1, 2, 4. So these are called the coefficients and the constant term. Okay, and here we've got 1 and 3. Now, we're going to go down memory lane, Ria. Memory lane, back to primary school, when we're going to do long multiplication. Do you remember how we did? Oh, you put your head back, but you'll see in a minute. So what do? We cover up the 1. Use the calculator. We cover up the 1, and we're going to go everything times the 3. The difference is we're not going to go 4 3s are 12. We're not going to put 2 and carry the 1. We're just going to go 4 3s, 12. 2 3s, 6, 1 times 3, 3. What did you do next? You remember? You covered up the 3 and you had to put a 0 here. Then you times everything by the 1. So 4 times 1 is 4. 2 times 1 is 2. 1 times 1 is 1. Now we're going to add up. 12, 10, 5, 1. Do you notice anything?
Why is it 10 and 12 instead of like 11 and...
So we're adding vertically. Yeah, look at that. This is your constant term. This is your coefficient of x. This is your coefficient of x squared. And this is your coefficient of x cubed. It's really cute and it works every single time. Okay? You will make mistakes with this. You would also make mistakes with this. But sometimes if you want to check an error, because it gets, you know what it's like, it just gets crazy and then you go, oh, I'm doing the same thing 5 times and I cannot find my error. Switch it up. Do something else and then you can double check. Do you like? I like. Ooh, nice spin. Okay, what if we have something like that? 1, 2, 3. How would we expand that? Elle's got an idea? Like you have the skills, right? This is nothing majorly new. Mia, you keep looking at your laptop. I'm being suspicious. So what could we do here? Well done. The first two. And you know what? You could do the first two. You could do the last two. You could do, oh, there's no middle two, right? You could do whichever pair you wanted. So Elan, you could go, oh, smaller numbers, I'm going to expand those. Tom just goes, nah, I just want to do the first two. I'm actually going to do the back two because I'm going to leave that 3x plus 1 at the front. It doesn't matter, right? Remember, 2 times 3 times 4 is the same as 4 times 3 times 2, any order you want. So how can we now expand this quickly? 2x times x, 2x squared. If we are confident with our timesing, we've got minus 2x, take another x. So you can just go minus 3x. If you're talking to someone next to you, if you've got one eye on your Swifty tickets, then you might not be concentrating. So negative times negative is a positive 1. And now we can do just what we did before with the times, times, times. Or we could do the synthetic multiplication. So we're going to do that one. We're going to just try it one more time. And then you can check with the long expansion. So Luca, what will I put for my timesy timesy? The coefficients. Yeah, good chap. We're going to go 2 minus 3, 1. And then we will times it by 3 and 1. Yep. 3 and 1. And we times out everything. 1 times 1 is 1. Minus 3 times 1 is minus 3. 2 times 1 is 2. You put the 0. Is that too quick? You put the 0. We cover up that 1. And we're timesing everything now by this 3. 1 times 3 is 3. Minus 9. Notice how you have to keep everything nice and neat in columns. 2 3s, 6. Okay, add up. 1, minus 3 plus 3, nothing. Minus 7, 6. So this is my constant term. That's the coefficient of x, x squared and x cubed. So I am predicting it's going to be x cubed minus 7x squared, no x, plus 1. Okay. So if we check this now, I'm saving you. You don't have to do all of this. I'm trying to be nice to you. Times everything by the 3x. So you get 6x cubed minus 9x squared plus 3x. Now times everything by the 1. 2x squared. Take 3x plus 1. Gather your like terms. There's only one 6x cubed. 9x minus 9 plus 2 gives me the minus 7x squared. We've got a plus 3x, take 3x, they cancel. You've got plus 1. So it works, right? Some of you will go, that takes up too much space. Don't like it, not going to use it. Fine. Right? Some of you go, oh, it's just no, it's there. Is that okay? Okay, Pascal's triangle. Pascal! Normally we bring in the lollies. Pascal's lollies. Bad luck, you got none. All right, Pascal's triangle, we start with a 1. The next row becomes a 1 and a 1. The next row, we put a 1, but then I put a 2 and a 1. The next row, I go 1, 3, 3, 1. What will I put for the next row? 1, 4. No, not 1, 4, 4.
5.
No.
3.
No.
1.
You guessed. So some of you haven't got it yet. What will I go for the next row?
1, 5, 10.
10.
10. 5, 1.
Okay, so fill in. Some people are still not getting. So who thinks they've got the pattern? Okay, go Tom. What do you think's going on here?
So it's just adding the ones above.
Yep, so 1 plus 2 gives you the 3. 2 plus 1 gives you the 3. 1 plus 3 gives you the 4. 3 plus 3 gives you the 6, and so on. Right? So just a pattern. So just to be sure, what's our next row?
1, 6, 15, 20, 15, 6, 1.
So back in the day, you could make year 8s do this and they just keep going and going, and then you ask them, look for patterns. All right, see what patterns exist in this sort of thing, and you could, if they get them to circle multiples of 3 or multiples of 5, and you get all these patterns and triangles, and then you get hockey sticks and all sorts. It's crazy, right? But lots and lots of patterns. You can see, yes, it's all 1, 1, 1, 1, 1. Then it goes 1, 2, 3, 4, 5, 6, 7. If you go through and circle square numbers, you'll see there's a pattern there. You go, yeah, yeah, yeah. But how does this relate to us expanding things? Well, you are going to discover that. Playing at home, we've just handed out the worksheet, which you'll be able to get in a minute. You can finish off the Pascal's triangle, but number 2, it's asking you to expand. Need my glasses. X plus 1 squared, and you can see we're going to do the x plus 1 cubed and then x plus 1 to the power of 4. We're going to do this long-winded. We'll do it together and everybody wins a prize. Pascal was a famous mathematician. He did a lot of stuff in maths. Even in spec we use some of his stuff a lot. Anyway, so we know x plus 1 squared is this. Yes, we expand it. We go the x squared. X times 1 is 1x plus another x, 2x, and 1 times 1 is 1. And you go, yeah, yeah, big whoop dook. I'll let you write. So now, to get the x plus 3 cubed, you could say x plus 1 times x plus 1 times x plus 1, yes? But how else could we say it? Wouldn't it be x plus 1 times x plus 1 squared, correct? Would you agree? And so we know that this is x plus 1 times x squared plus 2x plus 1. Yes, you were right. And now, you know, you can times through. So how do we expand this? Times everything in this bracket by x, then times everything by 1 and gather your like terms. Off you go. Okay, so happy with that? Everybody got? Now, you should be groaning by this point and me going, what about if I've asked you to expand x plus 1 to the power of 4? Now, we have 2 options of how to expand this. What are your 2 options so far? Yep. Good. You could go x plus 1 squared times x plus 1 squared. Or you could go x plus 1 times x plus 1 cubed, because you've got now your x plus 1 cubed up here. Or if you're using this, you've got your x plus 1 squared up the top. Does that make sense? So you are either, I don't care which one you do, you are either doing this times this. So if you've got a quadratic times a quad, well, what we did before, everything in the second bracket gets times by x squared, then everything gets times by 2x, then everything gets times by 1. Same, same. With this one, you would then be doing everything gets times by x and then by 1. Oops. What happens when you talk? We often say that maths is all about patterns, and I can now, instead of doing all of this expansion, I can do this pretty quickly. I can say that I know the expansion is going to be x to the power of 4 plus 4x to the power of 3 plus 6x squared plus 4x plus 1. Is that what you got? I would also be able to tell you that x plus 1 to the power of 5 would be x to the 5 plus 5x to the power of 4 plus, I have to go up and have a look, plus 10x to the power of 3 plus 10x to the power of 2, 5x plus 1. Right? Why? Giving you a bit of a tip, look at your expansions and then have a look at Pascal's triangle. So we're noticing here that our numbers here from Pascal's triangle are our coefficients. So it's 1, 2, 1. Yes? When we did the cubic one, it was 1, 3, 3, 1, which corresponds with our row here, 1, 3, 3, 1, and so on. And you will find that it all works the same way. Okay. However, we had a very easy one here where we just used a 1. So you're going to work through and find out what happens if it's not always 1. What's going to happen if that's maybe a 3, or what happens if this is an x squared and a 4x, whatever. You can find patterns to expand things really easily. That's the goal. Do we like Pascal? So if you turn over, I'm hoping that it is sort of explaining as you go along. Okay, so we're working through. If you get stuck, let me know. You can see that at the bottom of the page I start putting little boxes there that will make your writing a little bit neater and easier for you to work through. But you're just going to go through and discover Pascal. I love Pascal. Right, so rest of the lesson, you can either ask me any questions about your expansion stuff or working through with this sheet. We all good? Love you.